A few last words on the MAC layer. Everything we've spoken of today does not include any security. In particular, the broadcast nature with filtering by the destination means anybody can receive data, and this is how the MAC layer works. Some security mechanisms are added on most systems. For example, over Wi-Fi, the minimum that you require is a shared secret, a key, a password, which provides some form of access control, means you can control who accesses the network. Still doesn't authenticate. You're never sure whether someone is sending a packet and is exactly the one whom he or she pretends to be. That's the minimum Wi-Fi, the one you use at home. At EPFL, we do have authentication on Wi-Fi. Before connecting to the Wi-Fi network of EPFL, your system must provide credentials to your Gaspar password to the EPFL system. That will then authenticate who you are and give you access, and will map the MAC address of your device to this authentication for the rest of your association with this Wi-Fi network. Some Ethernet networks also do similar things. They are called MACsec, but it's not widespread, and wired networks are typically less attacked and also less protected. So it's not done at EPFL, for example. There is no MACsec at EPFL, but some entities can do the same thing as we do if we have the enterprise-grade authentication over Wi-Fi. We can do it also over Ethernet. When we have such security measures, the MAC frame header is typically not encrypted. That means it's sent in the clear. In fact, this is necessary because there is a type that explains that there will be encryption. And so what is encrypted is the thing we've seen last week, which contains, for example, the remaining type. So there will be, again, a type field. The type field says, this is an Ethernet frame that contains authentication. So inside this frame here, there will be another type field that would say, for example, it's an IPv6 packet or something else here. The MAC authentication and encryption material contains also some information that's sent in the clear, and that may be sent in a header and also at the end of the frame here. So this is for encryption. The encrypted part is only the MAC payload, which means the addresses are always visible. If we authenticate, which typically we do if we encrypt, the authentication covers the MAC payload and the MAC source address here. Knowing this, assume you are at EPFL, you connect to the Wi-Fi of EPFL. Now, thanks to the labs that we do, you know how to set up your computer as a bridge and connect a friend to your computer that works as a bridge. If you do this, will you be able to give access to someone else to the EPFL Wi-Fi network? I close the poll in a few seconds. And there is a tie between A and C. So of course, and the correct answer is C. It will not work. At least that's when last time we tried, it did not work. Of course, you need, if you connect here to the network, you're bridging the Wi-Fi. So you become part of the Wi-Fi network as a MAC layer. Remember, a bridge is transparent. So it will be the same as if you are connected, in fact, to Wi-Fi, even though you do it via an Ethernet port here. And of course, then you must, when BART connected with DHCP, he obtained a number of information. We know there are 4 configuration items we need for an IP system to work. So of course, this is required. In particular, Lisa should configure an IP address and a network mask that makes sense. But that's probably easy to learn and to guess. But it will not work because of the authentication of the MAC address. Lisa, if Lisa manages to get the IP configuration right, the packets transferred by the bridge here will appear with Lisa's source MAC address. That's one of the questions we've seen repeatedly with bridges. They don't alter the MAC addresses. Therefore, it will appear as somebody who's trying to is coming to the Wi-Fi network, but this MAC address does not correspond to any authentication data on the Wi-Fi infrastructure. So even if it will not have the MACsec header and trailer, even if we manage to somehow put it, it will be the ones that are obtained from BART that will have an incorrect MAC address. So that will not work. Fortunately, EPFL is well protected. Now let's try. Let's give it a second try. We've seen we can run our network, our PC as a bridge. We can also run it as a NAT. We can obtain a virtual box. We'll have a NAT inside the NAT. And then using IP masquerading function, we can a Linux host that runs as a guest in here. We can run it as a NAT. And we've seen also in the lab how to physically connect to the internal machine. So if we configure this, will it work? Closing in a few seconds. Closing. Then the majority says B, which is probably the correct answer when we tried it that worked last time. And the reason it works is that, well, first, the configuration is easy. The NAT software will typically give us also private addresses. So the configuration part is not an issue. And the NAT will make sure this is hidden to the rest of the world. And the authentication will also work because, in fact, for the rest of the world, there is no difference whether it is Lisa that is doing this or it's another process inside BART's machine that is connecting to the network. So that will work. So as you see, access control can easily be defeated if somebody is able to set up a NAT function. Voila. That's all we will see about the MAC layer. We have seen that the MAC layer for wireless medium takes care of sharing the radio waves in a local environment. The MAC layer for wired medium was originally designed with a similar thinking, and in such a way, it uses a protocol called CSMA-CD, but for wired medium now, it has got rid of that and uses interconnected bridges. And bridges can be used for not just for solving the Ethernet shared medium cable problem, but also to interconnect systems of any kind. We have seen 2 mechanisms to interconnect devices, the network layer with IP routers and the MAC layer with bridges. What are the differences? What do you think you could list as differences, right? Of course, they are different. They are not the same. But if from a philosophical viewpoint or for an architectural viewpoint, what are the main differences? Any idea? Well, scalability. Bridges will use forwarding tables, I should say, not routing tables that are not structured. So it must search the entire table for every packet, and it will not scale if we do that on a large network. So bridges work for small networks only. But now they have a benefit that they're independent whether IPv4 or IPv6 is used. They're plug and play and independent of IP numbering plans, which is, of course, one of their main use today. Voila, that's the end of this chapter. Any questions? No. Then without further ado, we move on to 2 layers above in the hierarchy of layer. We go back to level 4. We were at level 2. We climbed 2 stories. And now we'll talk about the transport layer. This I'll say at the end. We've already encountered the transport layer, and we know its goal. Its goal is to make the network available to software. So it gives an interface to program it. And there are two instances in TCP-IP, UDP and TCP. We will speak about QUIC later. QUIC is formally using UDP. So at least in this chapter, I will just describe UDP and TCP. There is IPv6 and IPv4, but there is no TCPv6 or UDPv6. The same TCP and UDP are used over IPv4 and IPv6. That's the good news. So that we don't need to redo everything. We have seen that UDP uses port numbers, and the reason for that is to be able to multiplex the data between multiple processes, or in the simplest form, there can even be several entities inside a process. For example, when you connect to a DNS server, your client, DNS client, will obtain a port number from your local operating system, 1267, for example, and will go to the well-known DNS server port, 53, which is well-known in the sense you expect every DNS server to have follow this convention, use port 53. Similarly, when we go to a web server, we expect the web server to reply on port 80 or 443, depending on whether it uses HTTPS or HTTP. And if it does not, then you must have some out-of-band information to get the port number of the server. For example, if you go to a server because you are following a link that's on an HTML page, the link can give the port number. So that must be well known by mechanisms other than the transport layer itself. And we have seen, of course, that the UDP header contains the UDP source port and destination port. That's the main information it contains. And this is used by the server to return the information back to the source. I used the word server several times. Perhaps it's time to spend a minute. What is the definition of a server in the context of the network layer? I close in a few seconds. The majority says D, which is the correct answer. At least if we want to be picky and formal, that's the correct answer. In the context of the transport layer, or the application layer as well, a server is something that is waiting for requests to come. In fact, it's the only way we have found for 2 machines to communicate. One must be started before and wait for things to come, and then another one can connect. Even in peer-to-peer systems, where 2 objects are at the same level, you cannot say one is the server, one is the client. But if we look at them in detail, we will see in the program that one of them is already started a socket in server mode, and probably both are in server mode because they must be able to receive. Otherwise, there's a bootstrap problem, right? We cannot connect 2 devices. One of them needs to shoot first, and if you shoot in a vacuum, nothing happens. So that's the server, and that will be visible in the transport layer, in particular in the socket. Of course, in the real language, in the informal language that we as human beings tend to use, a server is also the name that is often used for machines that host resources used in the network. For example, a web server, you call it the machine or a DNS server, you might give the name to the entire machine, not just to the role of a program. If we look at the UDP header, we'll find that there is a message length number. This is because UDP has the concept of sending a message and not a stream of bytes like TCP is doing. So the UDP service interface means the socket interface, the interface that you can use as a programmer when you use UDP. By default, it allows a message up to 64K, which is this number of bytes. And this is what will be delivered in principle. The UDP service, the UDP system will deliver exactly the message you've sent or nothing if the message is lost, which can happen. When I say the message, I make a subtle difference between a message and a packet. This is typically larger than a single packet, so it can be that a UDP message needs to be put into several packets. When this is done, strangely, this is the fragmentation of a big UDP message into IP packets that are smaller, is done by the IP layer, not by UDP. That's a weird thing. This is how things are in the internet. This causes what is called IP layer fragmentation that will be discussed in a few more lectures. We will come back to this point. So if a message is larger than the possible size for the IP layer, fragmentation occurs at the source at the IP layer, which means that the bits of header that are required to get all the pieces together, if you break a message into 4 pieces, you need to put information like what is the first, what is the second, or when you receive a piece, you need information in a header somewhere that tells you this is just a piece, this is not the complete message. So this additional fragmentation information is in the IP header. That's what we mean, it's done at the IP layer. We have seen also that UDP does not provide reliability, which means UDP guarantees that if something arrives, it is exactly what was sent by the source, but it may be lost, and it's up to the application to handle the loss here. For example, when we go to the DNS, the client resolver sends a query to a DNS server and starts a timeout, stop and go protocol, again and again. After some time, if the reply to the query has not come, then we decide that the message is lost and we send again. That's an example where using UDP is very efficient because I have a query response protocol. I have a protocol that asks a question and expects an answer. So we don't even need an explicit ACK because we expect an answer. So absence of answer is immediately detected as loss of a message. And this is how all UDP, this is how the simple UDP application uses the stop and go protocol ideas. How do we in practice use UDP? Well, there are many ways to do it, but most of them are imitating what is called the socket library, originally developed for the C and then C++ programming languages, but adopted by practically all other languages. In the lab, we use Python, and this is how it looks like. If you have a client and a server, they must do things a bit differently. Typically, a server or a client both needs to create a socket. A socket is a data structure in which you send and receive. And in the Unix operating system, it's very similar to a file descriptor. Writing into a file, writing into a socket is very similar. It is exactly the same in fact. On the server side, you need to call the bind. Bind, what does it do? Sorry, I should say first, when you create a socket, you need to say whether it's an IPv4 socket or an IPv6 socket. So I said there is no UDP 6 and UDP 4, but in fact there is socket 6 and socket 4. So when you create a socket, you must say whether you will be using IPv4 or IPv6. The protocol is the same in the sense that the headers we will see in the UDP packets are ignorant of whether they are sitting inside an IPv4 IPv6 packet, but the software itself is dependent. We have IPv4, IPv6 addresses. We must manage this. Then the bind allocates mainly the port, sometimes also the local IP address. Local IP address means the IP address of this host. Most machines have multiple IP addresses. Sometimes servers don't. They have only one single IP address derived, associated with their Ethernet interface, but probably those laptops have Wi-Fi and Ethernet. And if it's a Macintosh, it has zillions of addresses for all the purposes that Apple uses. So there is always in the operating system a default address. There's a rule of precedence. There is which address, which interface the system should use. Most systems do by default. If you're connected both to Ethernet and to Wi-Fi, we will use Ethernet. We don't use Wi-Fi unless we do something very special. But in principle, we assume Ethernet is better than Wi-Fi. So if you start a program that has both Ethernet and Wi-Fi, the socket will be bound to your Ethernet IP address by default. That's what the operating system does here. And that is what will happen on the client side. If you want to supersede the default, if you want to be sure that your server is not accidentally using an address that is not the one you would like to be used, then you can specify this in the bind here. So, but in principle, you don't do anything. So you give the 0 field, which means absence of address here. Then once the server has bound, so that's the address, and the server, of course, needs to say on which port number it is listening. That's not an optional, that's a mandatory field. There's no default for a port number. If this server is a DNS server, then it will do an S bind with port number 53. And then a server, that's the end of what the server is doing. In principle, somebody will send to this server, and sending a packet to a server is simply done with a send to primitive. We say send to and not send. That reveals the fact that we need two pieces of information, the message that we're sending and the destination, which is the IP destination address and the IP destination port number. So that is the argument of the send to. And then we do that a number of things. Of course, this is a toy example that sends only. That's a very rare example. In principle, when you send, you also expect a reply, and you will probably have a receive. And the server is showing also receive, and the dual of send to is receive from, which means when I do a receive, what happens? If there is nothing that has come, then I will block. So receive means, in fact, consume the next available message that has received on this socket. If none has received, has arrived, then it blocks by default. You can unblock it. We'll see that in the lab. There are mechanisms to, instead of blocking, saying, oh, it failed, and do it again. But by default, it blocks until a message arrives. When the message arrives, we get the message and the from, which means the source IP address and port number. That will be the result of this call. And of course, the logic is typically more complicated, but this is what happens here. So this stupid program here, if you run it in this way, will simply send one message, and this one will receive it and perhaps display it or something. Of course, this is a stupid program. It does not do what I claimed it should do, which is implement at least something like the stop and go protocol, wait for a reply to come, and if the reply doesn't come, try again. I said there is no UDP v6, but there is socket v6. So as we saw, we need to specify which protocol stack we use, v4 or v6. But the state of the art today is to write a program that will automatically choose one or the other. How can we automatically know whether we are talking to someone who uses IPv4 or IPv6? Well, we will find that a universal solution to this problem is to use the DNS. Because the DNS, all the layers except the network layer are in principle ignorant, or not ignorant, but work for both IPv4 and IPv6. And the DNS will. So for example, if I want to speak with lca.epfl.ch, I can go to the DNS by, for example, using one of the socket library functions, get address info, which here I've run it in the Python console. If I run this, here is the reply I will get. I will get this is how you go by software to the DNS, which means give me the IP address that corresponds to this name. And here I have two answers, and the answers also are saying to me which address type it is. So I have one v6 address, which is this one, and I have a v4 address, which is that one. So your server code typically does this before. And now if you obtain only a v4, then you have some logic to implement. If you obtain only a v4 address, for example, you have no choice, you go via IPv4. Same if you have only a v6 address. Now, if you have both, you have to choose which one you prefer. Many systems by default prefer IPv6 because it's more recent, that should work better. But it's not always the good choice because, for example, at EPFL, IPv6 exists only because we asked it for this course, which means the infrastructure, nobody really cares. The bugs are found only when you, in the lab, find bugs of IPv6 infrastructure that doesn't work because the rest of the EPFL community doesn't use IPv6. So it means IPv6 probably works a little less well here. If you're really serious about something here, perhaps if you want to minimize the bug and the tickets you have to put to 1, 2, 3, 4, might be a better idea to use IPv4. So some operating systems give support to find what is the best infrastructure to use. As far as I know, the Mac OS does this, so it will give you some hints, some functions that allow you to select which one is the best here, but that's more sophisticated. We're talking IPv4, IPv6. That's one of the nightmares of users or one of the benefits for network engineers, because it will always be a bit complicated. So there are mechanisms to try to simplify, but the presence of those mechanisms makes the story more complicated. For example, I said that a socket is in principle, we decide when we create a socket whether it's IPv4 or IPv6. The implicit consequence is that it cannot do both, but that is not true. An IPv6 socket can also work with IPv4. How is that possible? Well, if you have a socket that wants to receive or sends to an IPv4 address, then it does what probably the IETF should have done when developing IPv4, which is IPv6, which is make IPv6 simply a superset of IPv4. And this is possible using this block. So this block here, this prefix, lots of zeros, followed by 16 bits equal to 1, followed by 32 bits equal to 0. So there's 48 bits here that are equal to this. And here there's a block of also 48 bits equal to 0. In compressed form, this is how we can write it. Plus 96, that means there remains 32 bits that can be added to this prefix, which is exactly the size of an IPv4 address. So we can encode an IPv4 address in an IPv6 address by prepending to this prefix the IPv4 address. So if you have a socket that is an IPv6 and is allowed to do this operation over IPv4, then if somebody sends a packet to, if a packet comes to this machine here, it is possible to bind the socket both to the IPv6 address of the interface and the IPv4 address of the interface. So that's an example of a socket that's bound to two IP addresses because we need to manage both IPv6 and IPv4. Otherwise, in principle, you don't do that. A socket is bound only to one address. And the rest of the software here, when you write your program, because you've used an IPv6 socket, so in the code that you write, you will manipulate only IPv6 addresses. Right? If you put 32 bits in a field that expects 128, your program will crash somewhere. So the type of the addresses it will have will be IPv6, and this is entirely hidden. So it's a truly IPv6 socket, but it can talk IPv4, and this is hidden through this encapsulation mechanism of IPv4, this inclusion of IPv4 into IPv6. You could ask, why do we have FF and not just zeros everywhere? That's because there are multiple ways of putting an IPv4 address in an IPv6 address. We will see in the context of interworking between the two that there are other encapsulations that are used in different contexts. So since we have a lot of space in IPv6, whenever we do things differently, we give a different prefix. That's something we've already seen. That's the default behavior of most Linux systems, as far as I know, and can be run also on other systems, but by making it explicit. So that allows you, in fact, to be lazy and to have your program that runs only with IPv6. It works only if you still have dual stack in your machine. It means you have connectivity to the IPv4 internet and to the IPv6 internet. Right? You need both addresses here. That doesn't solve the problem of those who are sitting on an IPv6 only network and want to connect a machine that is only on IPv4. For this, we will see other solutions. And it doesn't work in the reverse direction. We cannot have an IPv4 socket that can be used in this way. We cannot bind an IPv4 socket to an IPv6 address because we cannot put something big into something small. Right? So the IPv6 address space is larger than the IPv4 space. So you could imagine compression mechanisms and so on, and perhaps some devices do that in some form, but certainly you cannot speak to the entire IPv6 internet over an IPv4 socket because the space of addresses, when you will do a send to, you will have only 32 bits to express to whom you're sending. So as far as I know, there is no existing dual stack IPv4 socket. So you see here, it's easy. I mean, none of this is rocket science. I have not shown any theorems with demonstrations, but it can easily be confusing. In particular, it's important when you look at things like this to realize that this is an IPv6 socket. Right? This is not an IPv4 socket. So an IPv6 socket, when you will program it, you will use the type IPv6 socket, INET6, and not IPv4, and it will manipulate addresses that are all IPv6. I mentioned socket as an abstract entity viewed from a programmer, but in reality, this is essentially a set of buffers. So to every socket is associated a buffer, in fact, two buffers, one on the sending side, one on the receiving side. On the sending side, because when the application program writes into the socket by using send to, then the software might not be able to immediately send it over Ethernet or Wi-Fi. Remember, if it's Wi-Fi, there is a CSMA-CA protocol that may take some time until the packet is available. Also, you may have hundreds of other programs like yours on the same machine that are sending at the same time over the physical interface. So there might need to be buffers. There are buffers certainly on the network interface card, but also on the operating system in the buffer, in the socket. And certainly we need even more buffering on the receiving side, because on the receiving side, when packet comes to a port number, so the operating system will know by the destination address which socket it should send it to, and by the port number, which of the several sockets that are bound to the same IP address, which it should send it to. And then it puts it into the IPv4 or IPv6 socket buffer, where it will stay until the application reads. There could happen bad things. Like, for example, you could have a denial of service attack on the socket where a lot of traffic is going into the socket here, and the application is not able to read very fast. What will happen in that case? Well, there will be overflow. The incoming messages might be lost, or whatever buffer management mechanism the operating system will use. If it simply uses the simplest form of management, when there's no space in the kernel, you drop whatever is coming. There might be other mechanisms, but this is the simplest of all. So that's another reason for losing packets. Now we will see how TCP handles this. If we bombard a server with, or a client with lots of packets, and the application program is not able to consume them quickly enough, then there will be losses at destination, which is the most stupid form of loss, because the packet has consumed all the resources at the source, on the links, the Ethernet, the network, the routers, and is lost at the destination because the destination is not fast enough. We'll see that TCP handles this, but UDP is not able to handle this. So it might be that if you go to a very busy DNS server, it doesn't reply simply because the packet made it through to the server, but the DNS software program is not fast enough to respond to all programs, so your request will be dropped by the arriving server. So similar things with a dual stack socket, except here we see that the same socket can be associated with multiple ports. I mentioned most of this, except of course there is this reassembly issue. On the sending side, the operating system sends the UDP message, which is sometimes called datagram as soon as possible, and the IP layer might fragment it into several pieces if needed. So on the destination, the pieces might come Of course, not all together. So you may need to wait until all the pieces of a common message has arrived. And if any of the pieces is missing, then the entire datagram will be considered lost and missing. So if you send a large message over UDP that is consisting of 10 IP, that causes 10 IP packets, if one of the 10 IP packets is lost, the entire message will be considered lost. It will not be delivered to the UDP socket. The UDP socket will not see it. So fragmentation is a bad idea. It would be better to know the size of the message and send smaller messages via UDP than send a big one, because you're taking the risk. You're increasing the chances that it gets lost. And the socket, in principle, is bound to one port, and it's bound to one or multiple IP addresses of the local machine, as we have seen. I think this one is clear. We can skip it. So that's UDP. There is not much to say, much more to say about UDP, other than exercising it in the lab, which you will do next. TCP is, of course, more sophisticated because it tries to fix all the problems that I've uncovered now, in particular packet losses. UDP application must handle that, but it's a smarter idea if we can have the transport layer do it, because it's a waste of time for the programmer to do it. So how does TCP manage the losses? Well, it guarantees that all data is delivered without loss, but worse than that, or better than that, depending on the viewpoint. It guarantees that the data is delivered in sequence. In sequence means that if you have an application program like old-style SSH, if you log in via SSH to a remote machine, and you type some characters, and the characters are echoed back to your machine from the SSH server, and which means for every character you type, there is one TCP packet that is sent to the server, who sends the echo back. That's when we are in this mode here. So here we guarantee that all the characters that you've typed here will be delivered exactly in this order at the destination, which makes sense for the application I gave, right? You're typing characters, you want them to come in the order you send. So how does it work? Well, it numbers all the data with a sequence number for every byte that you send. Not every packet, but every byte. Then we agree on some initial state information that we will essentially discuss now, which essentially means what is the initial sequence number between the source and the destination. And we wait for acknowledgements, very much like we did with the stop-and-go protocol. Here's an example of a TCP source on the left called A, a TCP destination B on the right. Time goes vertically, and A sends one packet. So inside the packet, there is a TCP header. Inside the TCP header, there will be information about the sequence number of the block of bytes that is contained in this packet. So here it's the numbers 8001 to 8500. The sequence numbering that we see in Wireshark, for example, is always such that the last number is the thing to come. So it's not the last byte, but it is the next thing to come, which means the size of the packet is the difference. We have here sending a packet of 500 bytes. When this packet is received by B, B will acknowledge it by sending a TCP packet that contains an acknowledgement. An acknowledgement is a TCP packet in the sense that in the TCP header, there is a field for acknowledgement and a field for sequence number. So here, in fact, if B has nothing to send, it means it is simply an empty TCP packet that contains only a header, and the acknowledgement field contains the value 8005.8501, which means it's the largest sequence number that I expect to receive next. Or in other words, it is a cumulative acknowledgement number. It means I have received everything since the beginning, whatever the beginning is, until 8000, until this number minus 1. So it means I have received everything. Then assume A sends packets, has 3 more packets to send. TCP has multiple mechanisms to detect losses. One of them is a timeout. So for every packet that is sent, a timeout is associated, like with stop and go. And assume those two packets here are lost, and assume that this sender here uses only ACK. We will see that a modern TCP machine sends other fields that would not make the thing look like here, but let's admit this for a second. If the only thing that is sent back is the cumulative acknowledgement the way it is done here, then the logic of TCP says if those two packets are lost, when I receive the third packet here, what I can acknowledge is the same as before, because the acknowledgement semantic is everything up to this number, excluding this number, has been received by me. So here, I have not received everything up to this number. There is a gap. So I continue to acknowledge only this one here, which, by the way, was useless because it's lost. An acknowledgement also can be lost, and TCP has to handle the cases where this happens. So in this case, the loss is detected by timeout. After some time, not receiving an acknowledgement for this block of information causes a timeout that causes the retransmission of this block or of other information. We'll see that later. Here, I'm assuming I'm resending exactly this packet. Now, when this packet is received, it's put into the socket buffer. Perhaps it's even already consumed by the application. And then the TCP will acknowledge everything that has been received, which means the first and the second packet. So it is acknowledging 9001, which of course is not acknowledging this packet. So there will be probably a retransmission a bit later, which is what we see here. There's a retransmission of this packet. And now, when this packet is received, we see that we received packet number 3 again. Now we can deliver everything, including packet 4, that was received, but could not be delivered. So here, packet number 4 was received. It's put into the socket buffer, but it's not visible to you and me when we use the socket. If we do a socket read, the application will say, no, there is nothing. We do it at this point. The application says there is nothing to read here. So you will block. You will block until you can consume here 500 bytes. And if you want to consume more than 500 bytes, you will block until this is received. And when this is received, what is made available is the block that has just arrived, plus the blocks that were here waiting in the depth of the socket buffer, not visible to you. This is what it means. TCP delivers packets in sequence. The TCP socket delivers only the data that have been received in sequence. Of course, the data that has been received and is not acknowledged, not delivered, is not lost. It is kept in the socket buffer. And we'll see that unlike TCP, unlike UDP, TCP has mechanisms for preventing that buffer, socket buffer's overflow. So it is kept and will be stored safely here. In practice, TCP is a bit smarter than what I said. I said that the acknowledgement acknowledges everything in sequence, but this is very limited. We see it on this example. So what TCP does is acknowledge blocks of information using field that is called selective acknowledge. So for example, when this packet has been received, B will send an acknowledgement that contains two fields. Here, the selective acknowledgements, and here one SAC block. There can be multiple SAC blocks in most current versions of TCP up to 3. That is explaining here, I have received everything up to this number, plus there is a gap, and I have received this thing here. Now, after seeing this, the source here would probably infer that there was a loss, because depending on the specific parameters of the source, we'll discuss that later. The source here sees that there is a gap in the acknowledgement. So in most cases, that means there is a loss. So here it might send everything that is missing. And you see here that we see the source is sending 2 packets in one. Right? It's sending those 2 blocks here in one. Why is this possible? Well, it is possible for 2 reasons. First, the IP packet size must be large enough to contain 1,000 bytes plus the header, which is probably the case in most networks. So we might wonder, why were packets here of only 500 cents? Well, perhaps because the application is sending 500 bytes at a time. We have an interactive application, for example, that does a write, sends 500 bytes at a time. Then TCP would probably try to send them as quickly as possible. So it is sending packets that are not full in some sense, small packets, half full packet. But when it resends something, TCP has no reason to send 2 packets, because sending 2 packets means more work for everybody, for me as a TCP sender, for the destination that will handle 2 headers, also for all the routers, and they will have the headers that will be duplicated, so more bits sent on the line. So of course you avoid this as much as possible. So we see an example here that is a consequence of what it means when we say TCP offers a streaming service. That means that TCP is allowed to rearrange the packets in order to fill packets that are as useful as possible here. In particular, when I receive this block here, I receive in one call, I receive packets that were sent in 2 blocks here, which means as a TCP application that is receiving data, you cannot make the assumption that if you ask TCP, give me all the data that has arrived in your buffer, you cannot make the assumption that this was sent as one block by the source. The delineation, the boundaries that might exist between blocks here are not respected by TCP. That's again what it means to offer a streaming service. So if you're sending, for example, a web page that contains an image followed by a JavaScript, and you send all of this over one TCP connection, then you must express somewhere, this is the beginning of an image, and this is the beginning of a JavaScript. You must put something. So this is, for example, part of the HTML language with MIME headers. You must put additional information to say, where does my message end? Where does it start here? This is not given by TCP. Unlike with UDP, when I send a DNS query to a DNS server with UDP, it knows this is one DNS query. It is not 3 queries merged together or half a query that was too large to fit in one item. Voilà, let's do a break before continuing to explore TCP. Let's have a look at the receiver side. Like with UDP sockets, obviously TCP uses receive buffer. And as I've mentioned, the part of the data that's in the receive buffer might be made invisible to the application because it's not received in sequence. That's the consequence of offering a streaming service here. But that poses a number of problems that lead to the necessity of having what is called a sliding window mechanism, which is the second ingredient beyond the axe of TCP. The problem that this solves is the following. Assume that you have repeated losses of the same block of data. Here I call them P0 to simplify the story, but we know the numbering is in fact per byte. So assume a source sends a number of packets. One of them is lost. No problem, they are still stored at the destination. But assume the loss of the same packet by mishap happens a number of times. Then what will happen is that the source will need to store a large amount of, might need to store a large amount of information. In fact, all the packets that have been received and that are now out of sequence, because we're trying again and again to send this. So we see that we have a problem of protecting the receive buffer. And protecting the receiving buffer is something that TCP wants to do. So we want to avoid this mechanism by preventing this from happening. How can we prevent this from happening? Well, we will say in a case like this, if P0 is lost, you're not allowed to send an arbitrarily large number of packets. You're not allowed to continue sending more and more as much as you want, because sooner or later P0 would be received. This is not allowed. Instead, we say there is a concept of a window at the source TCP. For example, here, the window is 4 blocks of 1,000 bytes or 4,000 bytes here. The window size, like everything for TCP, is expressed in bytes. And here it means that whenever a packet is lost, like for example, packet 0 is acknowledged, that's fine, that I can send. But here I'm showing that packet 1 is lost or sorry, no. When packet 0 is sent, here, I am allowed to send packet 1, 2, 3, but not more. So that if packet 0 is lost and will need to be repaired, I cannot move on here. Of course, as soon as I receive an acknowledgement for packet 0, I can continue. I'm allowed to send 1, 2, 3, 4. So the pink part here is saying all the, what I call the usable part of the window. Those are the packets that I'm allowed to send that are new packets. And if I have, for example, 12 packets to send, I'm not allowed to send packets 4, 5, 6, 7, etc. until, because they're not in the window. In order to send those packets, I must be sure that I have received enough acknowledgements. For example, here, when we're at this point here, we see that packets 5, 6, 7 have been sent. They have been sent here, 5, 6, 7, but not yet acknowledged. Why not yet acknowledged? Well, here there's no loss, but it may simply be that the destination is slow, or the reverse path of the network is slow. Remember, on TCP, we must work for all possible cases inside the data center at terabits per second and microseconds latency, or to New Zealand with megabits per second and hundreds of milliseconds of latency. So we don't know exactly what happens. It may be that the reverse path is slow. And in a case like this, then the usable part of the window here is just one packet. We see that we cannot go faster than sending one packet. For example, whenever I receive the acknowledgement for packet 4, then the window moves to 5, 6, 7, 8, which means I can send 8. Now I send packet 8, and then I need to wait for the acknowledgement of packet 5 to come in order to be able to send packet 9. So we see that in this case here, we have something very similar to stop and go, in the sense I send one packet, I can send one more when I receive one more. That's the so-called pacing feature of the sliding window that slows the receiver. Here the receiver has 13 blocks that are ready to be sent, but you see it takes a long time until it's able to send them. It needs to get the acknowledgements, enough acknowledgements back. And the reason is to make sure that the receiver has never more than 4 blocks into its socket buffer. So which are typical sizes. Socket buffer sizes are typical thousands of bytes, not more. You could say a machine has much more memory today than this, but you have many, many sockets, and typically those are the numbers that are given. So if we want to verify our understanding of the sliding window, at time t1 here, which is here, when so we have here a scenario where the source sends 4 packets. The first starts at 0, so I assume the acknowledgement, the cumulative acknowledgement is -1 and a SAC of 1. Then packet 1 was triggering this acknowledgement. Packet 2 triggers a similar acknowledgement. Packet 3 is sent, and we receive again this acknowledgement here. At time t1, what is the sender allowed to send? If the window size is, as before, 4,000 bytes, which means 4 packets of this size. I close the poll in a few seconds. And here we have B is the majority answer, almost unanimity. And we can see why. That's the rule of the sliding window. The window in packets is 0, 3 at time t1, because this has not yet, packet 0 has not been acknowledged. So we are blocked because of the loss of this acknowledgement, and packet 4 cannot be sent. Packet 4 will be able to be sent only when we receive an acknowledgement for something, for example, a cumulative acknowledgement that acknowledges everything and up to including 3. In that, we need this for sending the packet. We also see here that there is a receiving buffer, which in the case of TCP is also often called resequencing buffer. We see that the size of the window is exactly the size of the resequencing buffer. There will never be more in the resequencing buffer than the size of the window. So that's exactly the mechanisms that TCP uses to implement what is called flow control, avoiding overflow of the receiving buffer by controlling the size of the window here. But a fixed sliding window might not be sufficient to limit the buffer size of the receiver, because there is the resequencing size, the resequencing problem, but data might be perfectly in sequence, so there's no problem of resequencing. But there might be another problem, which is the mismatch of speed between the source and the destination at the application level. Typically on the server side, for example, that might be, if it's not very busy, it's very fast. If it's very busy, it's very slow. So you might have a case like this, where a source is sending a number of packets to a destination. There is no loss, there is no resequencing, everything is made available to the application, but the application does not consume them. So they're still stuck in the buffer. And we have again the problem that the slow application reads might cause a buffer problem and an overflow. So this is why in TCP, we have a window flow control with a dynamic window that is constantly being updated by the destination. This is called the window advertisement. The literature also calls this flow control. So the goal of flow control in general in computer networks means avoiding overflow between a source and a destination. So you don't want to do what I said is possible with UDP, that you send packets and that they are lost stupidly at the destination. With TCP, we avoid this by having TCP sending back to the source an information about the size of the window here. So here is an example. So in the fields that are present in the TCP header, we have the acknowledgement field. We've discussed this already. In addition, we have a window field. Here I'm putting round numbers. When we do Wireshark, we will see numbers that are much less nice because they're in bytes. Here I'm putting them in multiple of 1,000, and my packet size is always 1,000, which makes the story easy to explain, but in reality, it's not as nice. Here, a window of 2, that means 2,000 bytes here, means, as we saw before, that only packet 0 and 1 can be sent, assuming everything before 0 was acknowledged. Now, the source can send packet 0, which it does. It could also send packet 1, but before it has the time to send packet 1, an acknowledgement comes with the same window size, which means it can now send 1 and 2. And for some reason, shortly after, another acknowledgement comes with a larger window size. This can happen with TCP. We do see this in Wireshark traces, and we will see what could justify such a behavior in a few seconds. Here, that means the source is able to send packet 1, 2, 3, 4, which it is doing, 1, 2, 3, 4 here. And then as something gets acknowledged, the window moves by the acknowledgement fields. And we see that at one point, it is possible that we have sent all those packets and the window is not moving. The window is sent to 0 here. That's possible with TCP, which is saying to the source, stop sending to me because my buffer is full. There's no point you sending packets. I am not yet able to consume the ones you have sent before. And since TCP is offering a streaming service, anything you send now would just be stored somewhere, but I don't have space to store them, so they would be dropped. So this is a back pressure mechanism to stop a source here. Hopefully that doesn't last too long, and when the window size changes, another acknowledgement is sent with the new value of the window size. We have the same reason here. Why could that happen? Well, let's unveil what was happening at the destination that justified those strange changes in the window size. Well, I am showing here the socket buffer size, which I'm assuming in this simple case is just 4,000 bytes, and every packet is 1,000 bytes. 4,000 is a typical buffer size. Sometimes it's bigger, but not much bigger here. So the packets -3, -2, -1 have been received, and -2 and -1, so they've always been acknowledged. But -2 and -1, so this blue color means this data has been received, ACT to the source, so it can move the window, but not yet consumed by the application. So they're still using up some buffer size on the receiving side. And they will be freed when the application consumes them, which is done in TCP sockets by a read statement here. So here at this point, we see that the application has read not everything. So that's why a window size of 2000 bytes is acknowledged. Here, the application has sent everything. This is why if the local optimization of when TCP sends a packet allows, we'll send a packet that has a new updated window of 4. And here we see that the window size of 0 was sent simply because the socket buffer is full with data that is in sequence, no problem, has been acknowledged, no problem, but not yet consuming by the application, and it's filling the entire buffer. So we give a 0 to the source. Now, when the application reads it, then we free the source, we unblock it by sending a window size that is non-zero. So this is how it works. Of course, we need to be careful when we send a window of 0 because we are blocking the source. What are the bad things that could happen? Well, assume this, of course, if we block it forever, because we are truly blocked forever, that's the behavior, that's the expected behavior. If the server cannot consume anything from this source, it's right to block the source. It's better to block the source rather than let things be transferred and lost at the destination. But sooner or later, probably this will happen. But what happens if this packet is lost? When this blue, like the red, are TCP packets. Right? So it might be, and if it's an empty packet, then it might be lost, or even if it's a full packet. But if it's lost here, then this source is blocked. And we have what is called a deadlock. It is not sending anything because it's not allowed to send. And therefore, it's also not receiving any acknowledgement because the destination has sent this acknowledgement. And but this acknowledgement has been lost here. So to avoid this, the TCP standard says that even when the window is 0, you're allowed to send once in a while a 1 byte. You're allowed to send 1 byte in order to unblock the destination if it was blocked. Because of course, if the destination has nothing to send, it's a busy server. It's not monitoring whether the source is truly blocked or unblocked. So the destination will not actively remember what are all the 0 windows that have sent and should I unblock them. Instead, it will react whenever it receives something, it will send an acknowledgement. So in order to trigger this reaction, the source is always allowed once in a while to send a 1 byte. And if the window is truly 0, it will receive a reply. The byte will be discarded, and it will receive a reply that says the credit is 0, the window size is 0. But if something else was causing the deadlock, for example, a lost packet, then it will be resolved in this way. Of course, you must be allowed to send 1 byte only very infrequently. Otherwise, you might cause congestion on the server side. Let's put all those things together, because in reality, TCP is bidirectional. I've always shown A sending to B, but in quasi all cases, A and B speak in both directions. And so we have, if we analyze with Wireshark the TCP header, we will see sequence numbers, acknowledgement field, and window size. And here the sequence number means with respect to A's space of sequence number, whereas the acknowledgement and window are for B. So here I'm saying to B, when B sends, the window size is 6,000 for you to use for your window in this direction. And the acknowledgement is with respect to the numbering done by B. So A sends here 1 packet of 500 bytes and is acknowledging everything to 101. B sends another packet of 100 bytes also, and is acknowledging these 500 bytes that were sent by A and possibly other packets sent before, and also sends a window field to A. So those two things coexist in both directions here. We see here a packet that is lost. This packet is lost, and we see that in fact the loss will be here the loss will be repaired at this time here. And only when the loss is repaired, as we have seen, the bytes are available. Once the bytes are consumed, the window field here will be modified in this direction. So this is how TCP works. So TCP, compared to the stop-and-go protocol, has a sliding window. That's a major difference. In fact, we can consider TCP as a complexification of stop-and-go. With stop-and-go, the window size is one packet. I send one packet and must receive an acknowledgement to continue. So stop-and-go is TCP with window size corresponding to exactly one packet. We have seen that the performance of stop-and-go was limited by the round-trip time. Now, the question here is, how does the performance of something that TCP, how does it behave when there is now a window size which is not just one packet here? I'll close the poll in a few seconds. And the majority says A, which is the correct answer. In fact, is the only answer that matches the units, but let's see why. If the window size is large enough and there is no loss and no resequencing, then in fact, we will have a stream of packets that is being sent. So here I'm illustrating a case here. If you assume the window size is large enough, then the source can send, and it receives packets, acknowledgements, at the same rate at which it is sending them. So in a case like this, we will be able to use the total capacity. And if we look at things in detail, we see that what we need is, in fact, that the window size, which is illustrated here in bits or bytes, is equal to the available channel rate. So here I'm assuming one TCP connection that uses one channel for itself alone, which of course in reality will be a bit different. And the window size is the amount of data that can come here. So we know this as the bandwidth delay product, which is C times RTT. If in contrast, the window size is too small, then we will have a behavior that is somewhere closer to stop and go. We send, and then the window is too small, we're forced to stop, and we cannot use fully the capacity. Why do we discuss this? Well, because we see that, in fact, the window size is controlling the rate of a TCP connection. If I want, for some reason, this TCP connection now, which is not alone on this link, but is sharing the link or the server with thousands of other TCP connections, I may reduce the rate at which this connection is sending by reducing the window size here. And this we will discuss in the module on congestion control. So we see that the window size is an essential element of TCP, and is in fact essential for controlling the stability of the internet. It is essential for avoiding buffer overflow at the receiver, so controlling receiver buffer. That's the flow control function of the window size. We will see that we can even go beyond, and we can control how fast everyone is surfing the internet by playing with extra mechanisms on the window side. So this will come later. Like UDP, to use TCP, we use sockets. And TCP is simplifying the work of the programmer because you don't need to do stop and go, send an wait for an acknowledgement, etc. So it simplifies your work, but only as a second step, because the TCP socket is more complicated than the UDP socket. So there is always a law of conservation of complexity somewhere. The first thing, why is the complexity? Well, because TCP has what is called this connection concept. before being able to send data, in all the diagrams I've said before, okay, Siri has been fired. In all the diagrams I've shown before, I have shown things like the first packet is acknowledging everything that was acknowledged before. And I could do that because I was drawing the thing. But in reality, we never know this, except we agree on the beginning of things. So before sending data, before TCP to be put in operation, we need to synchronize the beginning. So we need to push a start button here. So this is done by an exchange of at least 3 packets, 2 in one direction and 1 in the other direction. So before being able to send, the source will send a packet that contains no data that must be acknowledged, and then the acknowledgement itself may be acknowledged. And it's only here in the 3rd packet that we're able to send data here. In practice, very often, we don't even send in this packet here. So this will guarantee that whatever acknowledgement field is coming, we know when things start. Essentially, this is solving the problem of knowing when things start. For reasons that would be too large to explain, it's not a solution to assume things should start at 0 always. In fact, we will see that the starting number is in the start sequence number is better to be random to avoid attacks in particular. So that's one thing, which means that when TCP connect, in order to send data with TCP, we use what is called a TCP connection. What does a connection mean? Well, the word connection means very different things depending on the setting. So it's a word we need to be careful with. Here in this context of protocols, things like TCP, connection means 2 things. It means there is state information, and the state information is somehow prepared, synchronized. UDP does not have state information. If I send to a DNS server, I don't need that this DNS server is particularly waiting for me to do something. In fact, this DNS server might not know that I exist before it receives any packet from me. So it is connectionless. There is no state relative to my interaction with the DNS server if I use UDP with the DNS server. With TCP is different. Before transferring a request to a server with TCP, we must prepare this server and put it in a state. Essentially, the state says what is the initial sequence number that I am expecting, and also that the server is expecting from me, and that I should be expecting from the server. And since we keep state information, whenever we keep state information, we open a potential problem. This problem is state information consumes resources. So if you consume resources, what is the effect, in particular on servers? Well, if you open a connection and someone else open another one, and if you never close the connection, then those resources will continue being used. So the software is aging, it's becoming clogged, and this is why, I mean, this is one of the well-known problems in software engineering. When you create data in languages that don't have automatic garbage collection, for example, then your program probably sooner or later will crash because it has been used for 3 months uninterruptedly. There are resources that have not been freed, and this is called, well, this will cause sooner or later the resources to be unavailable. So it's important also to release them, and this is why TCP connections need to be released, and in order to free the resources that are being used. Of course, there is automatic garbage collection in some cases, but not always. You may want to have a TCP connection that lasts for weeks or months between A and B. So there is no good answer to when we should release automatically the connection. Here is the TCP header. So before the TCP header, there's the IP header, which is 20 bytes for IP4, 40 bytes for IP6. And the TCP header itself is at least 20 bytes. We'll see that in the first packet, it's always more because there are options. What does it contain? Well, like the UDP header, the source, destination, and destination port numbers. but also the fields we've seen on the diagrams, on the cartoons I've shown a few minutes ago. Sequence number, which is 32 bits, acknowledgement number, that is 32 bits, and a number of options that are more or less useless. Some of them, some of the flags we will see have nothing to do with the transport layer. They are called congestion experience flags. They have to do with a congestion in the internet, so we will talk about them a bit later. And then options. An option is, for example, the negotiation of the packet size, which is typically done on the first packet that is sent when we open the connection. With UDP, we said things are fairly simple. A UDP message can be any size up to 64K by default, can be changed, but by default, that's the principle. And if it's larger than the size of an IP packet that is available on the end-to-end path between source and destination, then it will be broken into smaller packets, or it will fail in some cases. And that's up to the application to manage the chaos that might generate. TCP thinking is, of course, different. We do everything for the application. So TCP in particular will choose a packet size which is as large as possible in order to be efficient, while avoiding any kind of fragmentation. So a TCP packet should never be broken into pieces. So in order to do that, then there is the negotiation of the MS maximum segment size, which is done at least between source and destination. There's a number of other pointers that are typically very seldom used, like the urgent pointer, that is not so much used. How do we use TCP with sockets? Well, the beginning is very similar with UDP. This is a server side. The server starts open the socket here, binds. For example, that's a server that's listening on port 5003. So it will say so. And then the client will start a socket and send a packet to 5003. In fact, you cannot simply send a packet because, as I said, we need first to establish this synchronization of state. So you need to do a first thing, which is called connect. So we connect to the IP address of the destination, to this port number. And while doing this connect, this has the effect of sending this packet. So a SYN packet is a packet that has, I mentioned the flags in the header. So one of the flag is this, the SYN or the or not SYN packet. So a SYN packet means an empty packet. Whoops, this is here. ACK means there is also a flag that says whether there is an ACK field in the TCP packet. Every TCP packet has an ACK field, except this one, except the SYN, the very first packet. So the acknowledgement will acknowledge this packet here. If this packet is lost, or if the SYN ACK is lost, then there will be detection because the SYN ACK has not arrived. That's the usual business of TCP, and the SYN will be sent again. Now the SYN, similarly, if the SYN ACK is lost, then there will be absence of ACK of the SYN ACK, and the SYN ACK will be sent again. At this point, the two ends of the connection are able to send packets. Now, if we look at the server side, there is an intermediate thing which is called S1 listen. Listen means I am ready to receive SYN packets. And accept means I go to the queue. There's a separate queue for TCP for the SYN packets, which are connection opening requests. And when I am ready to really open a connection, I do an accept on the TCP socket, which means consume. It's only when I do the accept that this three-way handshake will take place. Like for UDP, it's blocking if no SYN packet has ever been sent to this connection. That's why the dotted line here. As soon as the SYN packet arrives, the SYN packet is consumed by this call. This generates this SYN ACK and ACT and waiting for the ACK to receive and resending, blah, blah, if all of this is happening. And only at this point, we have opened the connection. So we are at this point here. And the special thing with TCP is that if we look at the syntax of the accept, it returns something which is a socket. So here, when I say s1.accept, it means, as I said before, consume a SYN packet, but it means also something else. creates another socket, that's the pink one, and con is the identifier. In C, it's a pointer to it. In Python, it's the identifier of the object that we can use to work on that socket. And this is now another socket on which we can do what I explained before, receive or send data. So I can do send. I don't do send to, because I don't need to specify to whom I am sending, because this has all been done here in this connect here. When a TCP connection is established, it works only for a pair of source and destination. So you don't need to specify whom this is coming from and to whom this is sending. This is static information now for this connection. So I do a send, I can do a receive, and of course I can do a send on both sides or a receive on both sides. And when I'm done with my job, I need to close it, which will free the resources here. Why do we do this here? Why do we create another socket? That seems unnecessarily complex. Well, the reason is that if there would be only one client speaking to this server, probably we would not need to create this socket. But in reality, this is not how things are. The server is typically speaking to a large number of clients. So the server will, in fact, create a socket, and when the socket is done, it will fork and come back to create another socket. So in practice, it will have a large number of sockets that are handled in parallelism or pseudo-parallelism. True parallelism if there are multiple cores, and pseudo-parallelism if multiple of those connections are handled on the same core. So this is the typical case, even on single core machines. We use parallel threads of execution to handle several TCP connections, which means that on the server side, there are two types of sockets, the blue and the pink one. And they are different in the sense that the blue one is often called non-connected. Non-connected, that means that what the blue socket is doing is waiting for a SYN packet to come. That's very similar to the behavior of a UDP socket. A UDP server socket is waiting for a datagram to come, doesn't know whom it will come from, and that's exactly what it is doing here. In contrast, once a SYN packet has been consumed, the pink socket is connected. It is associated with all the data, port numbers and IP addresses of source and destination that were exchanged during the connect case. The operating system, very similar to TCP, has a buffer for every socket. But here the buffer is used more intensively. We've seen that UDP datagrams are just put in the UDP receiving buffer in whatever order they come. Here, of course, there will be a resequencing function put in the buffer. But other than that, it is the same here. The UDP sockets are different than the TCP socket. So if you send to port 53 over TCP or to port 53 over UDP, those are two different sockets. And different programs, or the same program, may be listening to these sockets here. We see also that the SYN packets are consumed by the unconnected TCP socket, so typically a server socket that is waiting for requests to come, and the connected sockets are used by the server for serving a given client at a given point in time. I have already mentioned this fact several times. So what we call a TCP segment is the most oftenly used word for TCP packet. We've seen that the unit of information exchange at the delivery layer, which we can in general terms call a packet, sometimes it's called a PDU, protocol data unit. PDU means packet. And the word packet is most often used for IP packets. And for the MAC layer, we say frames. For TCP, we say segment. So a segment, a TCP segment, typically sits in an IP packet, which itself sits in an Ethernet packet. So a TCP header contains all the data that we've seen, but deciding when to create a segment is the job of TCP, not of the application. We have seen an example before when TCP was retransmitting 2 packets of 500 bytes. and decided to make them into one packet. It was TCP that decided this, not the application. So it means that as an application, you cannot make any assumption when you receive data that the data has been written in this form by the application. In particular, for example, if you know a bit of C and you exchange a string of characters encoded in C, you know that in C, a string of character finishes with the null character. Otherwise, it's just random binary data value. Now, assume you have a big string of characters you send with TCP. How can you read this when you receive this? If you know it's a string of character, you don't know where the 0 at the end will be, except if there is a MIME header or something that says the string is of length so much and it goes on. But if you're just doing a basic program that sends a character string, you have to read character by characters on the receiving end until you see a 0. It would be a mistake that would crash your program. And in fact, that's one of the sources of attacks to gain control of program, is to create code that will behave in this way. It would be a mistake to have a program that says on the source side, send a character string, right? Make sure it's not too long, so there's never fragmentation. And on the receiver side, do forever read as many data as there is and print them on the screen. And if you're unlucky, you might be reading half of a string. That would cause printing and garble. In other cases, you might be reading multiple strings that will have a 0 at the end, might be less bad, but that could cause problems. That's the downside of using TCP. TCP offers a streaming service. You don't know what the data is. And if you're sending character strings, the only reasonable way to read this is to read them 1 byte at a time, 1 by 1. So you have to do calls where you consume 1 byte at a time, which of course is not very nice. TCP segmentation offloading is also a function where this fragmentation is typically a collaboration of the operating system and software on the network adaptation, network interface card, or even hardware on the network interface card. So to simplify the hardware, in modern operating systems, in particular in servers, perhaps not so much in laptops, but in servers, will tend to not do segmentation at all at the software level in the operating system. Will accept packets of extremely large size, even of size larger than any possible IP packet, will transmit them to the Ethernet adapter, and it is the Ethernet adapter that will do the segmentation. But here it's even worse. Even if you know how to instrument your operating system, you might not even know who is deciding about the packet size. It is the hardware at the time that it is sending it. TCP offers a streaming service, as we've seen many times. This has a side effect, which is head-of-the-line blocking, right? If one packet sent by A is lost, all data following this packet is delayed until the loss is repaired. For what types of applications might this be a problem? To have some context, so HTTP1 is the older version of HTTP, so used for the web, that optimized everything by doing one TCP connection per object. So a page must typically multiple objects, text, then there are links that says insert an image here, so that's a second object. There might be a JavaScript somewhere to display an advertisement or whatever. So those are multiple objects. And with HTTP1, you have one TCP connection to put all the objects. With HTTP2, you have one TCP connection per object. Of course, HTTP2 is more expensive, more connections, more work, but PCs are more powerful now, and devices are more powerful. And the real-time streaming application that would use TCP, for example, your sensor application that sends a voltage reading and measures it every 100 milliseconds and sends new value every 100 milliseconds. Closing the poll. A short majority says F, which is a correct answer. In fact, well, HTTP2 is more efficient in the sense, or with HTTP1, we have the head of the line blocking, which is that if you download a web page and the web page says, first thing is to display a banner with an image and say one of the packets of the banner is lost on the way, then the rest of the page is not visible to the web browser that has to display this. So because you're missing one element of information, you block. That is the head of the line blocking, and that's a penalty if we use HTTP1. Sorry, that's the penalty that we have. Sorry, you can see. What did I say? I said one TCP per object. I said exactly the opposite. HTTP1 is one TCP connection per object. I just said the opposite of what I meant here. So if we have one connection per object, of course, we have the head of the line blocking. And the same is true for real-time applications. So that's why many real-time applications don't use TCP. Imagine you're sending one sensor reading every 100 milliseconds, and one is lost. Then TCP will insist on making sure that we've repaired the loss of this measurement before delivering a new one. But the semantics of many such applications is that we're interested in the newest information. We're interested in repairing losses. If you send me a sensor reading and it's lost, my application has no visibility, would like to repair the loss. But perhaps the best way to repair the loss is to repeat it if no new information is available, or forget it and send the newest available information, which TCP will not do. TCP will not do that. The newest information will be blocked behind the old one that was to be sent. So this is the head of the line blocking problem. We will see that this exists with TCP. There's no way to avoid it. This can be solved by having one TCP connection per thing that you do. And this is exactly similar to what we'll see with QUIC. Before we leave for today, some announcements. This is the week of the online course evaluations. The process changes a bit every year, but what doesn't change every year is that the teaching committees complain that there's not enough responses to the online survey. So please do take it, whether you like it or not, but it's important that there's plenty of responses. Next week, I have a strong conflict of interest, so I will not be able to be here in this room at this time. So I will be replaced by our invited guest star. Stefan will do the course next week. Thank you for your attention.